Hello students. Now today we are discussing a very important points, that is the mechanism of the Sn reaction. So we already know the meaning of Sn reaction. I will repeat. What is Sn reaction? Sn reactions are nucleophilic substitution reactions are called as Sn reaction. Sn reaction is of the two type. Sn reaction is of the two type, Sn1 and Sn2. When Sn1 means it is a unimolecular nucleophilic substitution reaction. It is a unimolecular nucleophilic substitution reaction, and Sn2 means bimolecular nucleophilic substitution reaction. So this is a Sn2 reaction. So it observed that Sn1 reaction is a unimolecular nucleophilic substitution reaction, and by the kinetics, by the chemical kinetics. So what is the chemical kinetics? So chemical kinetics is a branch of the science from the chemical kinetics. Chemical kinetics is a branch of the science. It deals with the rate of the reaction. So when Sn1 reactions are observed experimentally, it observed that from the chemical kinetics, the rate of reaction depends upon the concentration of the only one, that is the substrate in the reaction. It depends upon the concentration of only one, that is the substrate. Okay. So therefore we say that this is a unimolecular reaction, as it depends upon the concentration of the only one molecule. I say in simple, only one molecule, and that is the substrate. Okay. So therefore it is a unimolecular. Now Sn2 reaction, from the chemical kinetic, the rate of reaction depends upon the concentration of the substrate as well as the nucleophilic reagent. As it is a nucleophilic reaction, so it depends upon the concentration of the substrate, means here the concentration of the alkyl halide and the nucleophile. So on both these reactions depend. So therefore this is a bimolecular reaction. So it is clear. So what is meant by Sn1 reaction? Sn1 reaction is a unimolecular nucleophilic substitution reaction where rate of reaction depends upon the concentration of the only one substrate, and in case of the alkyl halide, the substrate is the alkyl halides. In haloalkanes, the substrate is a alkyl halide. So here the concentration will be depends upon the alkyl halide as well as the nucleophile. Okay, so this is a Sn2 reaction. It observed that the Sn1 reaction is a two-step reaction. It observed that Sn1 reaction is a two-step reaction. So why the Sn1 reaction is a two-step reaction? Because as a rate of reaction depend upon the concentration of the only one substrate. Okay, and in the reaction the substrate as well as nucleophile is there. So substrate is only participate in the first step. So of course the nucleophile will participate in the second step. So therefore Sn1 reaction is a two-step reaction. Now Sn2 reaction is a one-step reaction. So how the Sn2 reaction is a one-step reaction? Because in Sn2 reaction the rate of reaction depends upon the concentration of the substrate as well as nucleophile, and both are involved in the same step. So there is no need for the further step, and therefore Sn2 reaction is occurring only one step. So like this way, Sn1 and Sn2 unimolecular nucleophilic substitution reaction and bimolecular substitution reaction, it is called as that one indicate rate depend upon only one, two indicate the rate depend upon the two. And Sn1 reaction is a two-step and Sn2 reaction is a one-step. So like this way, this is the basic thing about the nucleophilic substitution reaction. So what happens in nucleophilic substitution reaction? So when you consider the general representation of the nucleophilic substitution reaction, in nucleophilic substitution reaction, the nucleophile will be bonded with the carbon. This nucleophile is bonded with the carbon of the substrate with the lone pair of electron. And the nucleophile here is the X minus, which will be removed here by the attachment of the nucleophile. When nucleophile will be attached to the carbon of the substrate, the X minus will be removed. The X minus will be removed is called as a leaving group. So leaving group is also gone with the lone pair of electron, and the nucleophile is also attached with the carbon of the substrate with the lone pair of electron. So this is happen in nucleophilic substitution reaction. So that point we consider. Now we are discussing the unimolecular nucleophilic substitution reaction and the bimolecular nucleophilic substitution reactions in a detail with the suitable example and mechanism. So let us consider the bimolecular nucleophilic substitution reaction first. So now consider Sn2 reaction, that is a bimolecular nucleophilic substitution reaction. We consider first. So what is the example? So according to the chemical kinetics, from the kinetics we know that the rate of reaction is depends upon the concentration of the substrate as well as nucleophilic reagent. So these things we already discussed, nucleophilic reagents. So first we consider the example. Now example for the Sn2 reaction is a methyl bromide when reacted with the aqueous KOH or NaOH. From aqueous KOH and NaOH, the OH minus is the nucleophile I can use here. From aqueous KOH or NaOH, you get methyl alcohol plus Br minus. So here you get a methyl alcohol or methanol from methyl bromide. So this is an example of Sn2 mechanism. Okay. So rate of reaction here from the kinetics, rate of reaction is depend upon the substrate, that is a methyl bromide, and the nucleophilic reagent as a NaOH. So this is a Sn2 reaction is a bimolecular reaction. If I remove the proportionality sign, I have to place the constant, and here I can write like this way. So therefore it is a bimolecular reaction. Okay. Now let us consider the mechanism of the reaction, how this reaction can be occurred. So let us write the mechanism of the reaction. So the methyl bromide here I consider is like this way. So methyl bromide I can represent by considering the Weiss formula. In the Weiss formula there are the four type of the in the Weiss formula there are the three type of the line. Some lines are the normal line, some of the are the dash line, and as well as the solid line. So like this way these are the representation in the Weiss formula. Okay. So now where the nucleophile OH minus will be attacked. As we know that Sn2 reaction is a one step reaction. So the whatever the reaction step is a RDS. RDS means it is a rate determining step, where rate can be determined. So it is called as a rate determining step. And remember, rate determining step is always slow. So this is a methyl bromide. When the nucleophile will be approaches toward the methyl bromide, we know that bromine is also good nucleophile, or bromine is also having the negative charge. OH minus is also having the negative charge. So both are repelled. So in order to avoid the steric hindrance, the backside of attack of the nucleophile can be occur in the transition state. So I can show the transition state where the backside attack of the nucleophile can be occur. So this nucleophile can be attacked from the backside in order to avoid the steric hindrance or the crowding. So what is mean by crowding? Crowding means there is a bulky molecules are there, and because of the bulky molecules the carbon will be having the crowding. So therefore it is called as a okay. So what happened in this reaction? The carbon is with the 3 hydrogen. Now they becomes sp2 hybridized with an bond angle of 120. Now carbon here will show with the pentia coordinate state. Now the negative charge now will be partially divided in between both bromine and, so here the half negative charge with the bromine and half negative charge with the oxygen. So like this way, partial negative charge will be given on the both the chlorine and bromine. So the one charge will be now here divided as a half. So this is a half positive negative charge and this is a half negative charge. So like this way, one negative charge will be divided in between here. So remember, this is a transition state. So what is the important point in the transition state? Here, in the transition state, the CBr bond is a not break completely and COH bond will be not formed completely. The partial formation, I show here partial formation and partial breaking of the CBr bond. Now we know that during the formation of the bond, energy will be released. And in order to break the bond, we have to given the amount of the energy. So the amount of the energy released in the partial formation of the COH, it is utilized to break the CBr bond partially. So like this way, in the transition state, the making of the COH bond and the breaking of CBr bond will be takes place simultaneously by the using the amount of the energy evolved during the formation of the COH bond to break the CBr bond. Looks like this way. So making and breaking of the bond will be takes place simultaneously. One terms or one situation will become when CBr bond is completely break by the formation of the COH bond, and at a resultant of this, whatever the product you obtained in which the OH is now exactly in the opposite side of the here, as the OH will be approaches exactly the opposite side. So the OH is here. Now carbon with the 3 hydrogen are like this way. So in the when this happen, the exactly the opposite product will be obtained. Means here the OH will be attacking exactly this side and this carbon is exactly inverted. So this is called as a inversion of configuration. This is called as a inversion of configuration. Configuration, it is arrangement of an atom or group of atom around the carbon, and this arrangement of atom or group of atom here is exactly opposite. If you carry out the Sn2 reaction with optically active molecules in which there is a chiral carbon, the carbon which is attached to 4 different groups, and if such a optically active molecules if you consider and it allowed to undergo Sn2 reaction, then observe that the product here obtained is exactly the opposite side. So you can say that the inversion means reverse of the configuration is occur, just like the flipping of the umbrella in the heavy rain. In the heavy rain, if the umbrella is exactly in the inverted, so such a type of the configuration will be occur. So therefore you can say that Sn2 reaction is occur with the inversion of configuration. The configuration is inverted or it is a reverse. Okay. So what are the important characteristics test of the transition state? Now consider what are the important characteristics for the transition state. What you observe in the transition state? So the first thing is that when you consider the important characteristics of the transition state, the first is that here the backside attack of the nucleophile. So nucleophile, backside attack of nucleophile. The nucleophile exactly attack from the backside. The second, it is the one-step reaction. Again, the third is that the simultaneous bond formation and bond breaking is occur. Here simultaneous bond breaking and bond formation is occur. The fourth, the carbon in transition state, in TS, in transition state, the carbon is penta-coordinate. It is attached to 5 valency. So it is a penta-coordinate in which the carbon with 3 hydrogen, are sp2, in which the carbon with the 3 hydrogen are at angle of 120, are at an angle of 120. So they can maintain angle of 120 degree. So this is happen here, and the remaining pentatonic state will be off. And last point is that the product is obtained with the inversion of configuration. So inversion of configuration is observed with the product. Inversion of configuration is observed with the product. And this type of the inversion of configuration is called as a Walden inversion. Walden is the name of the scientist, and who will be invested this inversion, so it is called as a Walden inversion. So like this way, we have to remember the Sn2 reaction with a suitable example. Now let us consider the Sn1 mechanism. Now let us consider the example for Sn1 mechanism. So when you consider the Sn1 mechanism, so we know the meaning of Sn1. Sn1 means it is a unimolecular nucleophilic substitution reaction. So let us consider example for Sn1 mechanism. So Sn1, so where 1 is for unimolecular nucleophilic substitution reaction, means rate of reaction depends upon the concentration of only one substrate for this reaction. Okay, so let us consider the example. The example is that tertiary butyl bromide. You consider example for this is a tertiary butyl bromide. The carbon is attached with the 3-methyl group. So it is a tertiary butyl bromide. When reacted with OH from again NaOH or KOH, so it gives a formation of the tertiary butyl alcohol. Tertiary butyl alcohol. So this is an example for this reaction. So in this reaction, rate of reaction is depends upon the concentration of the only one, that is the substrate, and this is a reagent, nucleophilic reagent. So here it is depend upon the concentration of the only one substrate, that is a tertiary butyl bromide. This is a tertiary butyl bromide on which only rate of reaction is depends, and you get a formation of tertiary butyl alcohol. Okay, so from the chemical kinetics it is proved. Again, the Sn1 reaction is a two-step reaction. So let us consider the mechanism of the reaction. So in a mechanism, it is a two-step reaction. Two-step reaction. So what is the first step? Step number 1. In the first step, the tertiary butyl bromide. In the first step, the tertiary butyl bromide will be undergoes the heterolysis. Here the bond can be break. So heterolysis, because the carbon and bromine, carbon is a positive and bromine is a negative, so this bond is break. So in the presence of the polar solvent, the heterolysis can be occur, and it result in the formation of the tertiary butyl carbonium ion. I can show it by the 3 dimension. So like this way. So this is tertiary butyl bromide. So in which one is a with the Weiss formula and another is with the dash line. So this tertiary butyl carbocation is formed. So it is a tertiary butyl carbocation is formed, plus the Br minus will be there. So this Br minus will be there. So like this way, the formation of the tertiary butyl carbocation is the first step. It is RDS, so rate determining step, and it is a slow step, and therefore rate of reaction is depends upon only one, that is a substrate. What happened in the step second? In the step second, the tertiary butyl carbocation, now you observe, it is a sp2 hybridized because bonded with only 6 electrons. So it is sp2 hybridized. They are bond angle of 120. So therefore they have the plane symmetric arrangement. So in the second step, the attack of nucleophile. So as it is a symmetrical in the nature, so it is possible to attack the nucleophile from the both the side. The nucleophile can be attacked from the both side. As nucleophile can be attacked from the both side, there is a possibility that the OH can be attacked from the carbocation this side, or OH can be attacked the carbocation from this side. and this step is a fast step. Remember, this is a reversible step and this is a fast step. Okay. So at the result of the fast step, what happened here? The OH can be attacked from this side, then you get a product like this way, or the OH can attack from the opposite side and you can get a product like this way. So you observe that the position of the OH is exactly the reverse. The position of the OH is exactly reverse of each other. Here the OH is on the left hand side, here OH is on the right hand side. So like this way, exactly the reverse product will be obtained by the attack of the nucleophile. Okay. So you observe that here the Br is on this side and the OH is on this side. So what are the product you obtained? Having the configuration as the same as the reactant. So therefore I say that here the retention is same. There is no change in the configuration. And this product is obtained is exactly opposite. So here inversion is occur. So what happened here? Inversion is occur, here retention is occur. So 50% product you obtained with the inversion and 50% product you obtained with the inversion. So what is the 100% product for Sn1 reaction? So 100% product for is the 50% retention and plus 50% inversion. So the 100% is the racemization. Remember, the racemic mixture you obtained here and therefore it is called as a racemization. So Sn2 reaction is occurred by the 100% racemization because we know the racemic mixture. Racemic mixture is an equimolar mixture of the 50% dextrorotatory and 50% levorotatory. So here whatever the product you obtained, that product is obtained is a 50% dextro and 50% levo, and therefore overall is that the racemic mixture which is optically inactive is obtained, and therefore the Sn2 reaction can be occur like this way. So Sn2 reaction is occur in this two steps. The first step is the breaking of the CBr bond and formation of the tertiary butyl carbocation. In the second step, the nucleophile will be attacked from both sides and there is a 50% retention and 50% inversion of the product is obtained, and so therefore we can say that Sn2 reaction is occur with the racemization of the configuration. The configuration has a racemization. Configuration is a arrangement of atom or group of atom around the carbon. Okay. So what are the important characteristics transition state has? The first important transition state has a characteristic that it is a two-step reaction. Second, the reaction is occur in the two-step, out of which first step is the RDA step, where the formation of the tertiary butyl carbocation is occur by the heterolysis of the CBr bond. Second step is the attack of the nucleophile. At the result of the attack of the nucleophile, you get a product that is a 50% product with the inversion of configuration and 50% product will the retention of the configuration. So therefore, the reaction is occur with the inversion of the configuration with 50% only, and the 50% product is obtained as it is. So inversion of the configuration means if you take here a tertiary butyl bromide, at a place of tertiary butyl bromide you take any optically active substance, then whatever the product you obtained is 50% inversion and 50% retention, that is the racemization is occur. Like this way you get a product. Okay. So like this way we can consider the mechanism of the Sn2 reaction.